Um, it's my great pleasure to welcome here Gabriel Synnaeve, researcher at Facebook Research, who will talk about the StarCraft. And actually, we see that now we are working on the Atari games, but many people see StarCraft as the next challenge for the reinforcement learning because it requires more planning. And it seems that current state-of-the-art reinforcement learning algorithms are not able to produce good results on the games like StarCraft. So just welcome, Gabriel.
Thanks.
So go ahead.
Okay, so I'm going to present you a paper that we recently got accepted at iClear, which is episodic exploration for deep deterministic policies for StarCraft micromanagement. It's joint work with Nicolas Usunier, Zemigling, and Sumish Shintala. So yeah, you can find the paper on arXiv here, and the paper for iClear is a bit shorter, and you can find it here. I will give the slide after the talk, so you can also have the link. So okay, StarCraft. Just to give you an introduction to StarCraft, in case you are not familiar with it. So it comports several parts. One is you need to move the armies around across the map. So like large formations of units. You have some fights, so which is exactly the part that we are going to cover. The only part that we are going to cover in our research right now is how to micromanage the units, so how to make them more efficient in the battles. So that's just a sub part of StarCraft, of the full game problem. And then you have other problems which are, so as we will see now, scouting and the economy. So the economy is like, how do you gather the resources efficiently, and what do you do with them? What do you decide to build in terms of technology and army? So you need to build some buildings to produce the army, and you need to produce some buildings to be able to produce some other buildings or units. And also, like, the final difficulty of StarCraft is that you need to scout, because the game is partially observable. So you do not see basically where you do not have units. So you need to scout and send units around to see what the opponent is doing. Okay, so these are basically the main facets and the main problems and difficulties in StarCraft. And in our case, we will be dealing with the battles with what we call the micromanagement. So why do we take interest in StarCraft AI? So StarCraft is interesting for lots of reasons. So it's a very good game to study the interaction between learning and planning. It has complex dynamics, so it's called a real-time strategy game, but it has 24 steps per second. There is a large set of rules for how one step is going to change into another step, contrary to Go or chess, for instance. And the action space is very big. It's proportional to the army size, because all of the units can take different actions, so you have a combinatorial action space. The actions are durative, so it means that if you take an action at a given step, it's going at a given time, it's going to take several steps to have effect. So you should make use of the duration of the actions to break down the complexity of the action space. So as I said, it's partially observable, so you need to reason about what's happening under the fog of war, what you cannot see. So on this, it's similar to poker somehow. And so it's a good test bed for hierarchical reinforcement learning, for learning abstractions, learning the structure through the forward modeling. And another thing that makes it really interesting is that there are professional players and at StarCraft, in particular in Korea. And the current AI are very far from the level of the professional players. So I'm going to talk about some micromanagement tasks, so very specific control settings of fights that we studied. Even simple tasks are pretty hard, actually, if you want to deal with them without putting a lot of prior and a lot of biases in your solutions. Then I'm going to show the models that we used to deal with this kind of problem. The reinforcement learning baselines that we tried on this problem, which are Q-learning and reinforce, form of policy gradient. And then I'm going to present our contribution, which is exploration in the policy space, by opposition to exploration in the action space for deep networks, and our experiments and results. Okay, so we are going to study control settings that are like that, where we have a fixed number of units against another fixed number of units. They can be of the same type or different types. And the only goal is to beat the opponent during a control fight like that, a control battle. So here it's the simplest scenario that we have, which is 5 Marines against 5 Marines. So the Marines are ranged units, and yeah, average speed and low hit points. So what type of units and what types of command do we consider? So we consider 8 move commands per unit per frame. So for a given unit, we have this 8 possible atomic direction it can go to. And we have 1 attack command per enemy unit per frame that we can order. And so an attack will take several frames to have effect as a move command, actually. And so each unit has hit points and can inflict some damage when the cooldown is 0 and stuff like that. So it's like it's a real StarCraft. It's not a dumbed down version. It's just a smaller scenario of a smaller part of StarCraft only. The kind of scenario we have are like 15 versus 16 for Marines, 15 versus 17 for Wraiths, which are flying units, which have different properties, different acceleration, different cooldowns, different damages as Marines, and they don't have any collision because they are flying units. And we have Dragoon Zealots, which are 2 types of different units, like some melee units and some ranged units, 5v5 also. Okay, so there are previous works on micromanagement. Some dates back to 2005, concurrent hierarchical Q-learning by Marty and colleague. There are some work on straight-aware A-star pathfinding with some reinforcement learning tuned potential fields in Overmine, which was a Berkeley bot in 2010. Myself, I worked during my PhD thesis on StarCraft micromanagement with Bayesian influence maps, which are basically potential fields. There are also some works more on the tree search and heuristic search. So fast heuristic search in a simplified simulator by Churchill and colleague, which is actually, they have a simulator of the battles. And in this simulator, they do tree search to see which of out of a portfolio of different heuristics about what to do for the unit. So like which units to target or doing to flee, this kind of stuff. But they compute with the heuristics. They do a tree search to search for the current best heuristic for a given unit at a given state. So there are also some applications of tabular learning and SARSA with uncrafted features and meta actions. So like the actions that they use are very high level, like flee or attack or this kind of stuff. So that's the actions that they consider, not like the small moves and attacks. And the features that they have give some prior about the game as in the information. And so if you want to know more about StarCraft AI research, we actually have a survey paper on Tennant and colleague in 2013 that explains quite a lot of the bots up to 2013. So in our case, what we will have as input is the raw game states, not the pixels, and the actions, the previous actions that we took. And the output will be 1 action for each unit. So we have no, so I want to stress again that we have no access to the simulator, so we cannot run research because we cannot take the StarCraft game from a given state and simulate a lot of possibilities given the actions that we can take. So because we have no simulator, we cannot do Monte Carlo research that you can do, for instance, for chess or Go. There is an approximation, which is StarCraft, a simulation for StarCraft that I mentioned before by Churchill, Dave Churchill. But the approximation is actually quite quite different from StarCraft. So like the results are not so easy to translate from the approximation to the real game simulator, game engine. So there is no obvious featurization of the states and the action space. And we will make a featurization that I'm going to present, but it doesn't put any bias on the state. It just conserves the information of the state. Existing algorithms for deep reinforcement learning, they basically did not work well out of the box. So we tried deep Q-learning, which was very successful in Atari games. Of policy gradient, or kind of or high-level idea of why this existing reinforcement learning algorithms didn't work out of the box is because all the units must act in a coherent way. So if you look at Atari, for instance, there are 4 or 5 actions that you can take at each step, and so can you hear me all right?
Yes.
Okay. Yeah. So Atari, there are 4 or 5 actions that you can take at each step, and for StarCraft, as I said, it's combinatorial in the number of units. So for instance, yes.
We have a question.
Oh, go ahead.
Hello, Gabriel. Could you say some rules about raw game state if it's not pixels, it is?
Okay, so this, what we have is for each of the, so we have the map, we know the map, we know the elevation of the terrain, and we know which terrain is walkable or not walkable as a 2D array. And then for the units, we have their position. So we have a list of units. We have this unit is at this position with this many hit points, this cooldown, and so we have this. So basically, if we add the pixels, we could recreate the raw game states that we are using very easily. And because the pixels in StarCraft are just sprites. So we could have rules that say this sprite is this unit at this position, and that would be it basically. And on the other way, like the current worst game states that we have, if we add the sprites, we could just say from the states that we have, we put this sprite at this position, and it would generate the pixels. Okay, so there is a one-to-one mapping with the pixels.
Okay, thank you.
The only difference is that we are basically not limited in what we can do in type of models, because we don't have to have the pixels as input, and we are not limiting the viewpoint. We don't see under the fog of war, but we see more than one screen, because we see everywhere that we have units, we know where they are. Okay, and so yeah, the intuition of why current reinforcement learning approaches did not work out of the box is because in a coherent way, because of this big action space. So 4 or 5 actions for Atari, and you have 24 to the power 15 actions for StarCraft when you have 15 units in our current action space that we took to be very simple. And so in this case, basically when you are doing the exploration by sampling in the action space or by taking random actions, it's very hard to do structured exploration. So how do we deal with a large number of units? What we do is we do what we call a greedy MDP. So the classical MDP in reinforcement learning is you have a given state ST, you take the action A at T, AT, and you go to state ST plus 1 and you receive an immediate reward RT. That's a classic MDP. What we do is if we have n units, we will split the transition from ST to ST plus 1 in ST plus 1 over n, ST plus 2 over n, ST over n for the last units, which will be ST plus 1. So for each frame, we create as many intermediary states as units, and each unit plays in turn. We take a random ordering of our units, And what it has as input is the states that the state st plus the actions of the previous unit which already choose what they want to play. And so we go to the next game state and receive the reward after the last unit played for this frame. So we have st plus n-1 over n. Then this last nth unit plays knowing that. So knowing st plus whatever all the allied units played, and then we go to st plus 1. So that's a decision that we make about the inference. We could have a different inference process, but it works pretty well in practice. So the featureization that we use for StarCraft, so as I said, we have the raw game state, which is for each of the units, their position and their hit points, their cooldown, and stuff like that. So basically what we do is we do a graph between the units. Let's say we are choosing the action A for unit U. So we are this unit U, and we are considering one action, which is action A, which is to attack this opponent unit. What we will do is for each of the other units, we will say if it's enemy or ally. So we have a Boolean. Then we will say the type, which is a one-hot downgrading, the hit points, the shield, the cooldown, the current action type, and the next action type, if we know it. So that's when we know it for the allies, for instance. And then we will have the distances between all the units. So we have 9 distances, basically, which is the distance of this unit U to the A, this unit U to the U prime, for each of the U primes, the U prime to its target, and the U prime to its next target, this kind of stuff. So we have the distances between the action, basically the action that we want to take, and the relevant units that are important for our current unit U. So how does it go into the model? We have the raw input, which is for each of the units, we have the hit point position, target position, all of this stuff. It goes into the featureizer, which describes what I just said. Then we got the features, which is for each of the units, we have the hit points, the distance between its position and the position of its comrades, the position of the target, this kind of stuff. And this will go in a network. So this as input goes into a linear layer with non-linearity, and then another linear layer with a non-linearity, and then we do some pooling. We do both average and maximum pooling, so min and max pooling. And then these poolings we concatenate with embedding of the unit type. And we have then 2 more layers, and it will give us a score of those action. Or this given action. Okay, so this is for the modeling part, but how do we train such a model? So an overview of Q-learning. Q-learning is a joint value for a state and an action. So you have Q of S and A, which is a value. It should be representing the reward that you can expect for taking action A in state S. And so what we do is what like for instance DeepMind did on Atari games is that they represent this Q by a function which is a neural network, and they do what we call a function approximation for the Q, which is deep Q-learning. Sorry, and so how do you do exploration in this case? When you are at a given time t, you take action at, either with probability 1 minus epsilon to be the maximum over the actions that you can take in this current state, so maximum for Q. So that's basically what we call exploitation. And with probability epsilon, you do exploration. That's why it's called epsilon greedy exploration. You take a random action in the action space with uniform sampling. So when you do this, then you can do the update, which is Q at t plus 1. So this is the solution to the Bellman equation, basically. Q at t plus 1, theta at t plus 1 is going to be theta at t minus a learning rate eta, and the gradients with regard to the parameters is going to be the distance between your estimate of the Q of state T, action T, minus current immediate reward, minus gamma, the discount parameter, and the maximum value you could have had by taking the best action for ST plus 1. And this is squared because this is what you are minimizing is the root mean square error between the estimate of the value and the value you could get. So this is classical deep Q learning, basically. And the other baseline that we tried is reinforce, where you learn a stochastic policy. So instead of learning Q of SMA, you learn a model, pi of theta, that will give you a distribution over the action knowing the state. So that's what it means. We have basically a neural network, you see here, that takes the state as input and gives a distribution over the actions. So how do you do the exploration and the learning? Basically, you sample the actions in the distribution. So at the beginning, the model is random. So the actions are very random, like no special ordering in between them. You sample in them, and then the model will learn which actions are better, and then there will be more probable, and you will sample them more. So how do you update the weights in this case? You use the policy gradient theorem. So the theta at k plus 1 is theta at k plus a learning rate again. And then you sum over a whole episode from t equal 1 to big T, which is the end of the episode. So you sum so this is the discounting cumulative reward that I will explain after for a given T. But you multiply with the gradient of your model with regard to the parameters of log of pi theta a knowing s. So that's a log of your distribution over the actions in this given state. So this discounting cumulative reward basically is because now you are training in an episodic setting. Previously with Q-learning, you would train by having S at T, action at T, S at T plus 1, and the reward at T plus 1. That's what you need to update your weights. Here, what you need to update your weights is a whole episode from T equal 1 to T equal big T, which is the end of the episode. And so you will use the discounted cumulative reward, which is the sum of all the rewards you got during the episode multiplied by the discount, which is gamma. So in practice, we use gamma equal 1, so you could ignore this part, right? It's the sum of all the reward you got in the episode up until the current time step. Starting backward, so from the end of the episode to the current time step. Sorry. Okay, so both of these, if you remarked, what's really important in this is that how do you do the exploration? You sample in the action space. Here, sometimes you take a random action uniformly in the action space, and here you will sample still in the action space. So the difficulty of exploration is that if you sample in the action space and the action space is super big, you will have no way to structure the exploration at all. So an example to do that is, for instance, we took a model that was doing 99.6% win rate in 5v5 Marines, and we added 10% randomization over the action. And the win rate with just 10% of random action goes down to 75%. So if you add just a bit, so 10% is 1 over 10 actions that we take at random, instead of taking the best one, we lose 25% of win rate. So the performance decreases very fast when you add some randomness into action space, because the actions need to be structured somehow. So basically for tasks, it shows that either they are very easy because you can still do the exploration in the action space, or they start to be a bit big and then they start to be very difficult for these classic algorithms. And it's very hard to do a curriculum, so to do harder and harder tasks on a continuous way. So what we propose is to do exploration for deterministic policies. Basically, what we want is that if we are in a given episode and we have twice the same states, we want that the exploration in a given episode takes twice the same action. So we want the exploration to be deterministic. So there are some previous works on this kind of approaches, which is, so one is deterministic policy gradient, but it applies only to continuous action spaces because the randomness in the exploration comes from the fact that the action space is continuous and we have a discrete action space. There is some work on randomized value functions, but it applies only to linear models. There is bootstrap DQN, which we tried and benchmarked, but didn't work that well on our problem. The exploration is only through different initialization of the last layer of the neural net. There are some other works on exploration in the policy space directly, which is what we do. So it's for stochastic policies and models with few parameters. But we are very much inspired by this work, actually. So what we propose to do is to do zero-order optimization. The idea is if you have a deterministic policy, so if the action that you are going to take at t is always the maximum over some function of your parameters and the state and the actions, then like you are sure that if you are twice in the same state, you are going to take the same action. That's what we want. Then you have the cumulative discounted reward for an episode, okay, and you can, let's assume that this function is differentiable. Then what you can do is you can add a small random point on the unisphere that you sample, which is u, to your parameters directly, and you look at the cumulative reward over the episode of taking the actions with this set of parameters that you added this small noise. So the noise is u on the unit sphere, and you multiply it by a delta, which will control the scale of the noise that you add to your parameters. So you have this model with parameters, whatever, it's a function of some parameters. You add some noise, and you look at how it does in a given episode. And so if you do that, actually, you get an estimate of the gradients. So it's called zero-order optimization. Maybe some of you are familiar with it. Basically, you add this noise, just one noise, and you will get an estimate of the gradient. It's directly related to the definition of the derivative of a function, right? Which is f of x plus h minus f of x divided by h when h tends to 0. So that's the same here. You have a small noise. That's the same idea. And so what you can do is you can do gradient-free optimization, which is basically you update your weights to be your previous weights plus a learning rate time what you got here for the cumulated discounted reward that you multiply with the noise that you just added. So that's how you can update the weights and not have to do policy gradient, and you can still have a deterministic policy. But the problem with that is that you add some noise to your weights, and if you do that in a neural network, you transform a problem of doing exploration in a large action space to doing exploration in the policy space by adding some noise to the parameters, but you have a lot of parameters. So the dimension of the parameters is huge, and you didn't really solve your problem. So what we propose to do is to add the perturbation only at the last layer of the neural network. So if you see the last layer of the neural network, let's go back to the model here. So the last.
Gabriel, can you slow down a bit? We have a technical question. Can you return to the formulas, 2 slides back? Can you explain
this one?
What is U?
So U is you sample a point on the unit sphere.
Mm-hmm.
The unit sphere in the dimension that is the dimension of your parameters theta. Okay, so if we have theta in RD, that's U is going to be a point on the unit sphere of D dimension.
Mm-hmm. And delta is scaling.
Delta is just scaling, yes. Delta is going to control your exploration strength, kind of. If you have delta quite big, you will have a lot of exploration. If you have delta close to 0, you will be close to your actual model, so very little exploration.
Okay, thank you. But could you say some words? Why do you multiply by U at the as the next step. So you have like a little bit of
Yeah.
noise with this delta U, and yeah, here, and after that you just multiply by U. Why is that?
That's because that's how you want to update the parameters. So there are two ways to look at it. One is to look at like the definition of the derivative, right? Which is f of x plus h minus f of x and thus divided by h, with h going to 0. You can see the same with u. And if you want to update the parameters, in this case, you need to be of the same dimension of the parameters. So this is in dimension of parameters. This is in the dimension of the parameters. But if you want to put this in the dimension of parameters, you need to multiply by the dimension of u.
Okay, thank you.
That's what I mean. You can look up zero order optimization. That's a zero order optimization theorem, basically. So, okay, so we want to do that, but if we want to do that for the whole model, it's going to be much too big because the dimension of the parameters is huge. What we are going to do is to do this just for the last layer of the neural network, and then find a way to backpropagate the updates that we did for the last layer to the rest of the layers of the neural network. So, okay, what we do is we consider the policies of the form argmax of the dot product of some w with phi theta s and a. So what it means is that we have two sets of parameters, one for the last layer, which is a w, and one for the rest of the model, which is a theta. So this is for just the last layer, so it's maybe 100 parameters or 1,000 parameters, very, very small. And this is the rest of the parameters of the neural network, so it can be 50,000, 100,000, a million, whatever. And what we do is we sample this noise in the dimension of the w, and we play an episode where basically we do not change anything about the parameters of the neural network, but we add this noise to the parameters of the last layer. So we have some exploration in the state of the policy, but only in the state of the parameters of the last layer. And then we need to update the theta. So because we can use the zero order optimization that I showed before for the w, because we added this noise to the w, but we didn't add noise to the theta. So we need to have a way to update the theta. So we want to use backpropagation, which is the classical way to backpropagate the effect of a loss on previous layers in the neural network. So what we do is we do this, as I said. So we add the noise to the last layer, and then for each time step, we use RT times u as the ascent direction for the w following the zero order rule. And for the other layers, we do RT times u, and we do a pointwise multiplication with the weight of the last layer divided by the activation. So phi of theta is the activation of the layer before the last layer for a given state and action. So what does it mean? It means if we look at our model here we will have the w as an input for the last layer that is not shown here. And here, the activation after this last linear plus relu would be the phi theta, okay? So for a given state and action couple, the output of this is the phi, and the w is another set of parameters. So why do we do that? So why do we use this to backpropagate for the rest of the network? This r times u pointwise multiplication with w divided by the activation. The idea is this one. If you have the gradient of, with regard to x, of a function that is a dot product between x and y, it's basically f prime of dot product x and y times y. If you have the same gradients with regard to y, not x this times, you have f prime of x and y dot x and y times x. And so from this, we make the heuristic rule, which is not a theorem, which is not like well-grounded, but we make the heuristic rule that the gradient with regard to y of f dot product x and y is approximately the gradient with regard to x of f dot product x and y that you multiply pointwise by x divided by y. So it's not a real formula, but if you do that, you are in the same dimension, and these two formulas to indicate that that's a good multiplication to do. So x and y in this case are w and phi of theta. So that's how you update the parameter. Basically, you add some noise to the last layer of the neural net. You have the zero order update for the last layer of the neural net, and then you backpropagate this zero order, what it changed to the reward. So you backpropagate this r times u that you multiply pointwise with the parameter of the last layer divided by the activation of the layer before the last layer. Okay, so now the experiments. We have rule-based heuristics because we have very strong heuristics that actually are very often state-of-the-art in some of the bots that are competing on StarCraft. And we have the RL algorithms of deep Q learning and reinforced as baselines. What we look at is the immediate reward that we use for the update. It's damage inflicted minus the damage incurred between two states. So basically, the normalization of the hit points of our army and the hit points of the opponent's army. And what we do when we look at the results, we have some kind of test mode where we always take the actions with the highest score and probability for DQN policy gradient and zero order. What it means is that for DQN, when we test, we remove the epsilon greedy exploration. This way, we don't take these random actions that hurt very much the performance. When we do policy gradient, which is reinforced, we take the maximum action all the time. We don't do exploration when we do the test. And when we do zero order, we don't add the noise to the last layer. So it's like policy gradient. We take the best action. So the heuristics that we use, we have attack weakest, which is attack the weakest unit. So it gives focus firing, but it can do overkill. We have attack closest, which is also like attack the closest unit to the unit for which you are taking the action currently. And we have another heuristic, which is attack weakest without overkill, where we compute if we have already enough units attacking a given opponent unit. So these are some training curves for deep Q learning and for the zero order optimization in the simplest scenario, which is Marines 5v5. So in this scenario, we have just 5 units versus 5 units. And here it's the number of battles. And we can see that, so I think this one was done even with like a 0-1 reward, so like a reward of win or lost, not the reward that I shown before. And in this case, like deep Q learning over different initialization, you have very different behavior. Some of them are training pretty quickly, some of them are training slowly, and the difference in initialization makes it very hard to reproduce the experiment. And here, zero order over 5 different initialization, we have the same behavior of learning really fast. So here I'm going to show one model that was trained. So that's a 5v5 Dragon Zealot. We are playing the units on the left, and the units on the right are controlled by the built-in AI. And that's what it learned after a few thousand battles, the controllers, the policy that it learns to control. So you see that basically what happens is that the focus firing is pretty efficient from our model. Okay, so here are more quantitative results. The heuristics, we have a random target where we don't change it, no change. We have the built-in AI basically has no up. We have the attack closest, the attack weakest and closest, and the no overkill, no change, which is the weakest, closest, no overkill. And here we have the reinforcement learning algorithms. We have DQN, policy gradient, and zero order. These are the different setups. So if you train on these maps and you test on the same maps, what are the win rates? So we see that zero order does well on most of the scenarios. I mean, on all the scenarios. On this very simple map, Marines 5v5, everybody kind of, like, all the algorithms tend to learn a good policy. The DQN is optimal, zero order also. The policy gradient is close to optimal. But when you go to bigger scenarios, 15 versus 16 or 15 versus 17 race, you see that these kind of approaches don't work anymore because exploring in the action space, which is much, much bigger, gets much harder. So now there are a bit different experiments where we train on this map and we test on each of these maps with the model trained on this map. So if we train on Marines 15 versus 16 and we test on these maps, here I put just the best of the heuristics between parentheses, and here I put the reinforcement learning baselines. So what's pretty fun to see is that 15 versus 16, DQN actually has a very good test score when we test on 5 versus 5. And we looked at that. And basically what DQN learns is to focus fire, but with overkill. So if we look at the results here, it's pretty bad on this map. But when you look on 5v5, because there is no real overkill on 5v5, it has very good win rate. But when you look then at other maps, the win rates drops down. So the policy that DQN learns in this case is simpler than the policy that the zero order learns, which is to do the focus firing, but without overkill. So what we see here is policy gradient still also learn something that's worse than zero order and DQN. And yeah, zero order gets like pretty good results. And when we do the same for the race, so the race overkill is even more important because it takes less attacks from one race to kill another race, which are like the flying units. And in this case, so yeah, zero order also does much better. And if you look at the heuristics that are better, they are very different from the one here. So which means that the policies that you need to learn is different than in this scenario. And so now the last test that we did is to train the models on this map and test it on these maps, but also to play them against each other. So the first line, we see the win rate of policy gradient versus DQN. So policy gradient and DQN are kind of equivalent for the marine map. Basically, here they are close to 50% win rate. Policy gradient is doing better on the race map, and doing better on the race when it's in a balanced setting, but it's doing worse when it has to train on an unbalanced setting and test on a balanced setting. So because we train here the models in 15 versus 15 and then test 15 versus 15 and 18 versus 18 policy gradient versus DQN. Whereas here we train 15 versus 17 and we test 15 versus 15 and 18 versus 18 policy gradient versus DQN also. And what we see is that zero order bus works beats policy gradient directly, except for Marines 5v5. But all across the board, it's better. And zero order also beats DQN, except against on Marines 5v5. Okay, so the conclusion is that even simple StarCraft micromanagement scenario are complex benchmark for reinforcement learning, and we needed to come up with a new reinforcement learning algorithms that performs better than DQN and policy gradient. In particular, with large discrete action spaces where the exploration needs to be structured somehow. So we do the exploration in the parameter space, so in the policy space, not in the action space. The perspective on what we are working now is 2D ConvNet models, or also over the state, but you could see that would be very much the same as doing 2D ConvNet models over the pixels. We are merging the reinforcement learning with the recordings of human plays, and studying hierarchical reinforcement learning. So now I'm going to present you a bit of, so do you have questions about the reinforcement learning part? Because now I think I'm going to talk a bit about StarCraft and show you a demo of how that works.
So any questions about reinforcement learning StarCraft? Not yet.
Okay. Okay, so now I'm going to show you TorchCraft, which is the library that we use to connect Torch, which is a deep learning framework, to a Broodwar API, which is a way to send actions and get the state from StarCraft. It is available on GitHub here. There is a white paper and archive that describes the principle of TorchCraft. Basically, it's a C++ server that is running embedded with StarCraft. So you launch StarCraft and it launches a piece of code in C++. It will send over ZMQ the state of the game and take actions as input. We have a Torch client. So the usage is basically this. In Torch, in Lua, you say require TorchCraft. You connect to a host and a port. You can set up some settings and send the settings, and then basically you receive. When you receive, it updates the state of TorchCraft. You can featureize the state. You can pass it to your model. So if your model is a deep neural net, you can do forward of whatever. And then you send the actions to TorchCraft. And it will take these actions in StarCraft. And so recently, we have a new release coming soon. Basically, Jonas Gering ported most of the Lua client to C++. So you can also directly use TorchCraft from C++, or you can actually make a client for Python very easily because now everything is in flat buffers. So it's a developed branch on GitHub if you want to have a look at that. Okay, so now I can make a demo, I guess. So I'm going to show you how basically with TorchCraft and zero order we can train very quickly. So I set up here the scenario of 5v5, which is the simplest and that we train really quickly. And whoa, yeah. And so now, so here I'm training. Let's train a model from scratch. So it's connecting to TorchCraft. It's reloading the map. And so here is starting to train. So that's the number of battles here. Is it big enough or maybe?
Yes, it's big enough.
Okay. So we have the number of battles here. And so the win rate is here. Let's wait for 200 battles because after 200 battles on 5v5, it starts to have a decent enough model. And then I will load the model and show it play in live. So we are going to reach 200 battles soon, I guess. Yeah, so basically what it's doing right now is playing very fast, as we can see. So this is the StarCraft, where we don't draw all the frames so that the game can run much faster. We are at about 800 or 900 FPS frame per second. Okay, so here it saved the model. What we can do is, so okay, now we can load the model like that. I'd say take the last run best model, so which is the last model that we run, and let's run it slow. And now we can look at what it does. So on the left is the models that we just trained on 200 battles. So far it's not perfect yet. We see it just lost. So it's going to show. Okay, so it's winning this battle. So after like 200 battles, it starts to win a few of the battles, right? We have 1/2 right now, as you can see here, one win, 2 battles. Okay, so yeah, basically that's a demo. So this code of the reinforcement learning with zero order, we are going to release it as open source also pretty soon. I think before the end of February. Okay, I think that's the end of my presentation. Do you have questions?
Gabriel, can you return to your slide with perspective?
Yes.
And can you say a few words about every perspective and saying what particular problem you expect to solve with these new features in your model?
Yeah. So what we have in our current model is that basically we have a graph between the units. and the edges of the graph are the distances between the units. But if you do that, it doesn't really take into account the shapes, because you have a lot of different shapes that can lead to the same graph of distances. With the 2D ConvNet models, we want to have a look at how the shapes are important. One of the intuitions behind that, if you play StarCraft, is that some shapes, like a concave shape or convex shapes, are better than others for battles. And we wish to learn that with the 2D ConvNets. So where we put the units on a grid and we look at the shapes of the armies as like one more feature, kind of. So that's what we want to do with the 2D ConvNets. Why we would want to have this kind of models. So what do we do when I say merge reinforcement learning with the recording of the human? So we have replays. So basically the recording of the actions of humans in games, and we can look at which actions they take in a given state. So we want to have models that we can train both in reinforcement learning, as we currently did, but the same model we can try and make them predict the actions that the human would do in the current state. So if we predict the action, it's what is called a supervised policy model. And if we don't predict directly the action, what we can try is to predict the value function that led the human to take this action. If we predict the value function, it's called inverse reinforcement learning. And another thing is, if we just predict what is going to happen after a human take a given action in a given state, if we predict what is going to happen, we are training a model of the world. And in this case, we can use the model to do model-based reinforcement learning. So that's all the kind of stuff that we can do with the recordings of the human. And the last point is hierarchical reinforcement learning. So here, we just look at models where we have atomic actions, where we look at the possible moves and the possible attacks. But we don't reason in terms of have the army flee, for instance. One action would be make the army flee, or make this unit flee. But flee, it doesn't transcribe, it's not transcribed directly in which action you are going to take. So hierarchical.RL is how can we learn the concept of flee, for instance, or the concept of pursuit for a given army, in terms of how it's decomposed in lower level actions.
And for the last hierarchical RL, do you think about how to do you think to build it on top of the recording of human plays, for example, by subtracting some sub goals or something like this? Because as I see, if you are using options in your current approach, so for you, recording human plays might seems as a data where you can from which you can extract your options for further reinforcement learning on top of it.
So yes, there are two ways to learn the options that are pretty different. One is to look at the data of the humans, and from the data try to learn the options, which is not a reinforcement learning kind of way. It's just like, how can we clusterize the human actions into options? And another way is to both do the reinforcement learning and learn the options at the same time. So the action set would be, in the beginning, just atomic action. And then you can also learn to combine these atomic actions into options that you can take as actions, right? So these are like two different ways to learn the option. One is during reinforcement learning, and one is just observing the human play.
Okay, thank you. Any other questions? Okay, we have one more question here.
Okay.
Thank you for the lecture. I have a short question. Maybe I missed. What did you use as the reward function for your model?
So the reward function, I just said it briefly here. In the experiments the results that I showed in the table, the reward was the hit points of our army minus the hit points of the opponent army that we normalize. So so basically, the idea is that to win, we need the opponent army hit points to go to 0, and we need our hit points not to go to 0. So that's the basic idea behind it. And why is it normalized? Because at the beginning of the battle, if we just do the sum, like the hit points are much better much higher, right? So if we don't normalize it, we have a credit assignment problem between the beginning and the end of the battle. So we just normalize it over the battle.
And
the details are in the paper, by the way, if you want to look at the formula.
have you tried to use the reward function, maybe just one value if army wins or lose at the end of the game?
Yeah. So I believe that when I made this plot, it was this reward function, which is 1 if you win and -1 if you lose. So in this case, the training is longer because basically you have much sparser reward. So you need to win the battles before you get a positive one. Whereas the other, you need to start damaging the opponent army before you get a positive reward. But for a simple scenario, I think, for simple scenario, I know that you can train with what we call a 0-1 or -1-1 reward. For the larger scenario, I'm not sure that we try to train them with this kind of reward.
Okay, thank you.
Any more questions? No. So let's thank Gabriel.
Okay, and so I'm going to send you the slides if you want to share them with the.
Yes, please send me slides, and I will put them on the web page with the link to a recording of your talk.
Cool. Thanks.
Thank you again for accepting our invitation to give a talk.
Thank you. Thank you for having me.
Bye.
Have a good day.